So this is the second part of our compositions of transformations video, and we're going to use reflections and parallel lines theorem. So we're going to reflect the segment HG around line K and then reflect that around line M. So it's a double reflection in parallel lines. And so we're asked a few questions here, naming some congruent segments to HG, HB, and GA, and also is AC equal to BD, and what is the length of G double prime. Our solution, let's try this. Our solution here is that HG is congruent to HG prime, and it is also congruent to HG double prime. And HB is congruent to H prime B, and GA is congruent to G prime A. AC is equal to BD because we basically have two lines perpendicular to the same line, so the distance is congruent here. And since these two lines are also parallel, we've got opposite sides of a rectangle, so BD is equal to AC. And by the properties of reflections, since H prime B equals 9 and H prime D equals 4, then the distance between K and M is 13, and so the length of G double prime and H double prime is 2 times that distance, so it's 26 units. Let's try another one. So the graph of segment RS down here, if we do a rotation first followed by reflection, does the order of transformations matter? So here we have our original segment, RS, and then we first rotate it 90 degrees up here to R prime, S prime, and we come up to here to 3, 1, and 6, 2, and then we reflect it about the y-axis, and we end up here at -6, 2, and -3, 1. This is not the same as what we got before. If we look back, notice here we are here. So here's my green here at 3, -1, and 6, -2. Here we are here at -6, 2, or I'm sorry, -3, 1, and -6, 2 for our RS double prime. So yes, the resulting segment RS double prime is not the same. In the example 3 of part C above, that we're talking about this one here, what is the length of G prime, G double prime? Why is it equal to H double prime? It's because they're opposite sides of a parallelogram. So if we look back up here, we notice that G double prime is and H double prime are opposite sides of a parallelogram. Sorry about all that going back and forth. Let's try another one here. So we have a pre-image reflected in line K and then in line M describes a single transformation that maps the blue figure to the green figure. It is a translation to, it's a translation, right? We're just sliding to the right. And that would be a distance of 3.2 centimeters because the original distance between the two lines is 1.6. So it's going 3.2 centimeters to the right because the lines are perpendicular, and the theorem that says your distance between the two lines that you reflected about twice is the distance between the two figures are going to be twice that distance. Now reflections about intersecting lines theorem. If we have lines K and M and they intersect at point P here, then a reflection in K followed by a reflection in M is the same as a rotation about point P. So the angle of rotation 2x, where x is the measure of the acute angle or right angle formed by K and M. Here's my K, here's my M, and so that's x degrees. So the reflection of the line, the segment AB about K and then followed by reflection about M ends up being twice this angle. My original angle x is now 2x. So here we have these little fishes reflected twice here, about a 70-degree angle of these intersecting lines. The final reflection is going to be a 140-degree rotation about P. So here we have the diagram, the image, and the pre-image here. We have an 80-degree angle. So when we describe a single transformation that maps the blue figure to the green figure, it's a rotation, I didn't want to do that. It's a rotation of 160 degrees, about point P. And then second question, a rotation of 76 degrees maps C to C prime. The map of C to C prime using two reflections. What is the angle formed by the intersecting lines of the reflection? It's going to be half of that, 38 degrees. I'm sorry, C to C degrees. Okay, that ends part 2.